Okay, what we're looking at now is a Beckman Industrial Circuit Mate 9020. It's a 20 megahertz dual trace oscilloscope with a delayed trigger. Um, it'll handle 5 volts per division to 5 millivolts per division, and it does it in 10 steps, 10 range steps, and will cover 1 second per division horizontally to zero point 0.1 microseconds horizontally. Has a magnification times 10 on the horizontal and vertical, um, and also has a something called Circuit Mate, which allows you to do component testing and provides signatures of various components and gives you an idea whether the components are operating properly or not. The unit is attractive. Relatively light usage handling. Very, very minor, tiny dent right here. Slight abrasion in the paint on the back, but in general, front panel especially, quite attractive. Okay, let's just check out some of the basic features to familiarize ourselves with it. First of all, we have the power switch down here. We can see that the power lamp is lit. We have an intensity control. Take ourselves from full off to full brightness. Plenty of brightness there. We have a focus control. There's very sharp, blurred. Focus is working very well. And we'll trigger ourselves off of channel 1. Alright, so right now we're connected DC on channel A, channel 1. We can go to ground. We can go to AC connection, no problem. Our trigger control right now is lit. We are at the moment in auto. In auto, when we're not triggering, we still get a trace, but we can lose frequency, but in this case we didn't. We have AC, DC coupling, low frequency filter, high frequency filter. The difference here's AC coupling, AC, DC, low frequency. So here we're not permitting the high frequencies to come through properly, and then high frequency. And we're on channel 1 for the source right now. If I flipped it to 2, we'd lose sync or trigger. And if we go to the normal mode by the push of a button here, in normal mode, if you are not on trigger, then you're going to lose the waveform altogether. So it's only when your light is lit. So we lose the light, lost the trigger. So everything's working normal there. We're right now on channel 1. If I depress the button here, we're now looking at channel 2. So I have to move my input to channel 2. And then I need to move my source for my trigger to 2 and bring myself into range. Here we go. We're on DC. Here's ground. Oh, there we go. Had to put myself in auto mode for trigger. and then AC. So that's working right. And as we can see, our trigger, it's retaining trigger over the entire. There we go. Now if I put it in normal, we lost the trigger, and then as you lose it, then you lose the trace. But that's normal. We have an XY mode. We have the horizontal sweep frequency, time base. That's working fine. And you're going to see during the demonstration, the calibration, that our volts per division on both channels is right on. So much so that when I superimpose both the traces one on top of the other, you don't even know they're both there. They work together as one, and that'll be the proof that they're calibrated at least in unison. And then when I test against my calibration equipment, you'll see that it's accurate as well. At the moment, looks like we're looking at one trace. We're not. There's two. I can demonstrate that by applying a voltage. We're on 5 volts per centimeter on both channel 1 and 2. And I'm going to apply a calibrated voltage from this Fluke DC calibrator here. And we're going to go 10 volts. Alright. We've deflected 2 divisions. It's a nice sharp trace. But if I kill channel A, you'll see it fall out. I put it back in, or I can kill channel B. And the meaning is they've both tracked together, and they both overlay beautifully, and they both are reading 5 volts per centimeter. That's 10 volts, and 10 volts is what we put on. Reducing my scale to 2 volts per centimeter, and we'll apply 1 volt, 2 volts. Right, that's 1 division. 3 volts, 4 volts. There's 2 divisions. We're tracking together both channels, just like I said. Let's go ahead and change range again. We'll have to reduce our voltage. One volt per division. We should see a 1 division step. 2, 3. Perfect. Go 0.5 volts per division. We should jump 2 divisions now. 1, 2. No problem. 0.2 volts per division. We're going to go to the 1/10 of a volt step here, and that would put me half a step, whole step. We're at 0.4 volts right now. 0.2 volts per division, 0.4. Perfect. 0.1 volts per division, whole division. No problem. 50 millivolts per division. I'm going to actually go down another decade on my voltage source, and we're going to go 10 millivolts at a time. No, let's go 100 millivolts at a time. That'll be 2 steps. There's 2, 4, no problem. Alright, now we're going to go 10 millivolts per division. Here's half a division, whole, half, whole, half, whole. Perfect. 10 millivolts per division. We're going to go division, 2, 3, no problems. And finally, 5 millivolts per division. We begin to see just a little bit of noise, but no problem. We're going to go 2 divisions at a time. There's 10 millivolts, 20. And I could go to the millivolt at a time. Here's a fifth of division, 2, 3, 4, 5. Right on the numbers. 2 divisions, no problem. Alright, so we've established that our DC gain is beautifully calibrated, and we react properly with both channels at the same time. And now the thing to do would be to check the horizontal time base. Okay, at this moment, let's turn this intensity down just a little bit. At this moment, what we were doing is inputting a signal from this HP 3320 frequency synthesizer. And we're going to see if we travel across the tube in the appropriate amount of time to determine whether or not our horizontal time base is accurate or not. Okay. So what we're going to do is we're going to start counting as we see the beam appear on the screen. We're going to see if we have 10 cycles. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So we get 10 traces across the 10 centimeters of the screen. And this is at our setting of 1 second per centimeter, and we are feeding in a 1 hertz signal right now. So basically it's 10 seconds across the screen. You'll get a cycle every second. So we counted 10 of those cycles. Let's go ahead and turn this up. Alright, now we're 10 times higher. We're on 0.1 seconds per division. And what we see is we traverse the screen in 1 cycle perfectly. 10 divisions. Alright, let's kick this up again. We're 10 times faster now. Well, it doesn't do to have this generator running so slow, so we're going to kick it up 10 times. Alright, we have a perfect cycle across the screen, 10 centimeters at 10 milliseconds per division. For 10 divisions, that's 100 milliseconds, and that means we're running at 10 hertz. Alright, let's go up by another factor of 10. Alright. We're now running at 100 hertz. And again, perfect trace across the screen. We've got 100 hertz coming in. We're at 1 millisecond per division. 10 divisions is 10 milliseconds, so that would be 100 hertz for that period. Alright, let's go up another 10. Now we're running 1 kilohertz. Another 10. And I kick up my generator. Alright, we are now on 10 microseconds per division. We have 10 divisions, that's 100 microseconds. 100 microseconds is a tenth of a millisecond. And if we were at a millisecond, that'd be 1,000 cycles. If we have a period that's 1/10 of that, we must have a frequency 10 times higher. That'd be 10 kilocycles. And that is what we were at. All right, we're going to kick up our horizontal again. Factor of 10. We are now running at 1 microsecond per division. And that means I have to kick my my generator up again. And what we see is we traverse the screen in exactly 10 divisions, which would be 10 microseconds. And if we're 10 microseconds, then it takes 10 times longer than it would if it was a million cycles per second. So we must be running 100,000 cycles per second. Let's go up one more factor of 10. We are now at 0.1 microseconds per division. And center ourselves here so we can read it. There we go. And we see that we traverse the screen perfectly. Crosshairs here, crosshairs there, crosshairs there. And we are feeding a 1 megacycle signal in. And we are traversing the screen in exactly 10 divisions. We are at 1/10 of a megacycle per division, so it would take 10 divisions to get a single cycle. So our time base is very accurate. Let's go ahead and turn the lights back on. So now we've tested the vertical response. We've tested the horizontal response. Both of them are perfect. Both of them are tracking together. We've still... There, I just killed our channel 2. We're triggering off of channel 1, so if I kill it, we kill both. But there you can see we're tracking together. It's beautiful. And if we pull our positioning knob out, we get a times 10 horizontal adjustment. So let's see. That being the case, we should have 1 cycle across the screen. We do. We have 1 cycle across the screen, and if I push this knob back in again, we'll have 10. So that's working well. I can go channel 1 only, which is what we're doing now. If I was to right now, channel 2 does it. If I adjust channel 2 switch, you see nothing on the screen. That's because the only thing on the screen is channel A. If I go on channel 2, I can do that. Now it doesn't matter what I do with, well, it does matter what I do with A because I'm still triggering off of it. And there's both together. So it's a beautiful thing. It's working beautifully. All right. We have a 1 volt, 1 kilohertz signal coming into this unit from a fluke calibration device. And we're going to turn the frequency up. This is 1 volt at 1K, 1 kilohertz. Here is 10 kilohertz, 100 kilohertz, megahertz. Virtually the envelope is unchanged. The frequency is right on. So just to demonstrate that we are able to read the AC signal up through from 1 kilohertz to a megahertz and hold the envelope steady. Okay, so at this point I've taken one of my probes and connected it to the calibration, probe calibration test point on channel, we're using channel 2 right now, and as we can see we have the square wave for the calibration, nice sharp square wave there, and doesn't matter which channel I'm on. Right now we're connected AC wise. If I go to ground, you see that go out. If I go to DC, we see we're shifted positive of the ground line. AC, we're centered. That's the way it should be. Let's go ahead and put ourselves on the DC on channel 1. And, okay. And give ourselves a... Okay, there's channel 1. We're shifted positive of ground, and then going AC wise, same thing. So we have no problem with the calibration. Okay, we're going to demonstrate the single sweep feature. We're connected to the calibration point, so we have a signal coming in. We're going into channel 1, or A, channel 1 in this case. I've got the single sweep button depressed. My time division is set at 50 millisecond per division, so if I see a sweep go across the screen in 10 divisions, it's going to be 500 milliseconds, roughly a half a second. So let's go ahead and I'm going to hit the reset button for the sweep. We're going to see a single sweep happen across the screen. Okay, that's the single sweep function. We can do it again. There we go. So it'll demonstrate one trace across the screen. Not quite sure why you need that feature, but it's there. Okay, we've connected ourselves up to the external trigger. I have myself an external source for the triggering. I'm connected up to this Hewlett-Packard 3320 synthesizer. Right at the moment I'm feeding in a kilohertz signal, and I am triggering externally, and I can prove that because as I vary my my frequency here, you're going to see the signal lock in. There we go. So the external trigger is working. Okay, we have ourselves set up with a triangle wave coming in from our signal generator, and we are now in the delay mode under search. We can go with a delay, or we can go search. Right now I'm on search. So you're looking at the waveform triggering as normal. So I'm triggering at the peak of the triangle, and I'm getting one peak across the screen. Now when I go to, I'm doing this at a 10 microsecond per division rate. And if I introduced a 10 microsecond delay, then what will happen is I won't trigger at the peak anymore. I'll trigger 10 microseconds later, which is roughly this this point on the triangle, which is a division over. So let's go ahead and do that. Okay, let's put it in delay. All right, we see we went from the peak to that point in the triangle. That introduced a 10 microsecond delay. Well, okay, we have the Beckman 9020 hooked up using the component test inputs right now, and this circuit wasn't working when I got the unit, but it is working perfectly now, and we're going to demonstrate what it's all about. With this, you're basically turning the scope into a kind of a tracer, like a like a semiconductor curve tracer or something like that. I have a series of components to demonstrate what I'm talking about. Here we have a 100 microfarad, I think, no, 10 microfarad capacitor. We're going to hook this capacitor up into the circuit, and that's the signature for a capacitor. In fact, it's probably an electrolytic capacitor So the little bit of flattening on the top and bottom is probably characteristic of it. Here is a coil. We'll take a look at it here. I'm going to look at just one side of the coil here. And if you look closely, you'll see that it's almost a rectangle or a trapezoid. Small opening in between, and probably the higher inductance that you get, the further apart are the lines. Let's take a look at a resistor. Typical resistor. There's a signature for a resistance. Current and voltage are equal or in proportion. Alright, let's take a look at a Zener diode. There's a characteristic for a Zener. So in the manual is a page dedicated to signatures for different devices, and you kind of would study those signatures, and then reportedly then you can use this to help identify parts and maybe do diagnostics and so on. My own opinion is I haven't really seen too much of it being used. I don't know that much about it. I got the idea, but I'm not sure of the worth of it. However, certainly interesting to experiment with. All right, here's a it's a 2N3904 transistor, pretty common transistor, NPN device. All right, that's the signature for a for an emitter base, I believe. Base emitter junction. And this is the signature of the collector base junction. So as you can see, it definitely does provide you some distinctive signatures, and perhaps learning those would help identify the components you're trying to repair. If you didn't know what this little gizmo was it a transistor? Is it an FET? Is it something else? Is it blown? I guess there you might have a problem. However, the component test works fine. Was a little bugger to repair, but it's done, and I'm happy to be able to offer it to you. Now, let's take a look at two other interesting, not so much functions, but capabilities of the unit. On the back are two outputs, or excuse me, two BNC connectors. The one on the right that I'm plugged into right now says sweep ramp output. The one on the left says Z-axis input, and gives you some information on 30 volts peak to peak maximum on the Z-axis input. Sweep ramp output, I approached it cautiously because I wasn't sure how much voltage there was. But there appears to be something on the order of about 10 volts. I'm going to swing this thing around. We're going to take the component test off. There we go. And so right now we're sweeping across the screen. But on my scope over here, you can see the the sweep. Sawtooth type thing. I'm going to turn off the overhead light. There we go. Alright, right now I am on 2 volts per centimeter, and so I'm looking at 4 volts up, 4 volts down roughly, so 8 volts peak to peak. And as I change the horizontal time base on the Beckman 9020, you'll see the ramp change speed as well. Okay, so maybe you would ask me, what is this good for? Let's turn this to DC. We'll get a little bit better response on the low end. There we go. Well, if you had a voltage controlled oscillator and you'd like to sweep that oscillator, you would put this ramp into the input of the VCO, adjust your sweep time to what you wanted, and you'd be sweeping your oscillator. Could be very useful to have a swept generator. It's not so easy to come up with really nice ramps like this. So it's kind of a nice feature to be able to have that on the output. I'm not real sure about other uses, but I bet you if I thought about it some more I could come up with it. So, Z-axis input. We'll take a look at that next. Okay, I've connected a generator, signal generator, up to the Z-axis input on the back. And I have my Hewlett-Packard 3320 putting out a 10 megahertz signal, which is basically the white blocks you see. And I am imposing about a 200 hertz signal on the Z-axis, and as I vary the voltage of that signal, you're going to see like a shutter opening and closing there. So as the voltage changes, I'm going to change the period of time that the display is blanked. And according to the book, this will allow you to change the intensity of the beam. Not exactly sure why you'd need to do that, but I'm thinking that one thing you could do, I think I've seen done, is that you could, by utilizing the Z-axis input, create images on the screen in a raster scanning kind of effect, changing the intensity at the same time that you're scanning the screen. But I suspect that most of the time you've got little use for it, at least on the standard bench, maybe for the experimenter. But it's working. The whole unit is working. I'm quite happy with it. Thank you for listening to me. Oh, there is a manual that's going to come with it. Gives you the operating guidelines, gives you the component test patterns that you're going to get on the test inputs, component inputs, and circuit diagrams for repairs. That's how I repaired that component test circuit. So you'll have this. If that's not enough, I'm going to go also throw in a new set of 20 megahertz oscilloscope probes to go with it. Now, I'd venture to say there's darn few vendors on eBay go out of their way to make sure you've got a set of probes and a manual, along with a fully calibrated working scope. So, happy bidding. Thank you for listening. We'll see you again.